Hi everyone, so this is going to be a very important video and very conceptual video, and like 90% of the guys are confused in this particular topic. That's why I thought of making a separate video on this particular topic. So in this video we will try implementing a random Boolean functions, some random Boolean functions using minimum number of NAND gate and NOR gate. Minimum number of NAND and NOR gate should be used. Okay, it's not that if 4 gate can implement a particular function, then we will be using 5 gates. Not like that. Minimum number of NAND and NOR gate. Okay, so before that there will be some prerequisites. So can you replace your NAND gate by this gate? Because I told you NAND gate is bubbled OR gate. So this bubble will come up in front, right? This bubble will come in front, and this gate will be replaced with OR gate, right? Similarly, NAND gate is nothing but what I mean to say is NAND gate is, this is the NAND gate, and then there is another inverter. This is our NAND gate is, right? Sorry, basically what I was saying, what is our AND gate? NAND gate, then another inverter. So I just replaced this gate, and then there is one inverter. So can I replace my AND gate something like this? Do you agree to my point? Can I replace my AND gate something like this? Basically NAND gate and then there is an inverter. So NAND gate, there is an inverter. Similarly with NOR gate, this bubble will come in front, and this OR gate will be replaced with AND gate. And similarly, what is this? This is a NOR gate with another bubble. NOR gate with another bubble. So this bubble will come in front and it will be replaced with AND gate, and this another bubble can be replaced here. So this is how I can replace my NOR gate. So these examples I hope these are clear to you. If you are not able to remember this 2 and 4 points, then at least remember 1 and 3. These are very important. Bubble will come upward, bubble will come in front, and it will be replaced like this. So these are NAND gate can be replaced with bubbled OR gate, and NOR gate can be replaced with bubbled AND gate. Well and good. Okay. Now I will be using these two terms, SOP and POS. So SOP means sum of a product. Sum of a product. So this is a product term, no? A into B. This is a product. Plus C into D. So this is an example of sum of product. Sum of product. Sum of product. SOP. More example can be there. AB plus BC plus CD. Sum of product. Now we will see product of sum. Product of sum. So first we need to do the sum and then product. These two are the sum terms. Again we will discuss it when we study K-maps, when we study Boolean algebra. At that time we will discuss it again. But here basic prerequisite you need to have product of sum. Product of sum. You are doing the product of sum terms. These are the sum terms, or it can be replaced with A into B plus B into C plus C into D. So product of sum. So this is known as product of sum. So very easy thing. Sum of product. Sum of product. Product of sum. Product means multiplication. Now let's start our topic. So we need to implement random Boolean function using minimum number of NAND gate. First we will study about NAND gate, then we will study about NOR gate. So these are the points which you might not be able to remember, right? You might not be able to remember these points, but when I am talking NAND gate, you should always think about SOP, sum of product. So my target will be to implement the function in sum of product form. Basically in this form, sum of product, sum of product. This will be my target. When I talk about NAND gate, when I talk about NAND gate, my target will be sum of product. This is what you need to remember. So basically there will be a function. First we will implement that function using basic gates. Using basic gates we will implement that function, and then we will convert the basic gate into NAND gate. We will see the examples, it will be more clear to you. But do you remember for implementing NOT gate, how many NAND gates were required? For implementing NOT gate, how many NAND gates were required? How did you implement NOT gate using NAND gate? This is how you implemented, right? A and A bar. Only one gate was required. That's it. Right? For AND gate and OR gate, you might not be remembering the answer, but let's derive it. Let's see how we will be able to do it. So if I need to make a bar, how will I make it? Using NAND gate. Using NAND gate, I need to implement all these functions. So how will I make it? This is how I will make it. This is your A, but Y will be A bar. Now what do I need to make? I need to make AB. So implement AB using basic gates. How do I make AB using basic gates? This is how I make AB using basic gates. AB using basic gates. This is A, this is B. So Y is equals to AB. But you need to use NAND gate, right? You need to use NAND gate. Now tell me one thing. If I say my input is A and I want my output to be A only, and if I use one inverter here, so to compensate this inverter, I need to use another inverter, right? If I am using two inverter, then if I have applied A here also I will get A only. So similarly, I need to use NAND gate. So if you need to use NAND gate, here you need to add an inverter. So if I am adding an inverter here, I will have to use another inverter here. Say yes or no? Because if I am adding an inverter, then another inverter I have to use. So to implement this gate, how many NAND gates are required? This itself is a NAND gate, so 1. And to implement this inverter, how many NAND gates are required? Another 1. So what will be your answer? You need 2 NAND gate to implement this particular function. This we have already seen how we will implement. AB bar, and then simply both will go here, and that would be the answer. AB bar here, and answer Y is AB. So in this manner you can proceed. What is the way we are proceeding? Are you able to understand this point? First I have implemented it using simple basic gates, and then I thought what I need to do. Let's go to this example. A plus B I need to implement. A plus B. Okay. So how can I implement A plus B using basic gates? A plus B. That's it, right? A and B, my output will be A plus B. But what I need to use? I need to use NAND gate. So from here, if I need to make NAND gate, how will I make NAND gate? I have to use one inverter here. If I am using one inverter here, so to compensate that, I have to use another inverter here. I can use one more inverter here. To compensate that I need to use one more inverter here. What is this? This is a NAND gate only. Look here. This is a NAND gate only. That's why I told you need to remember it. NAND gate is bubbled OR gate. Why did I do this thing? Because I need to use NAND gate. So I am introducing a bubble here. So if I am introducing a bubble from my own side, so to compensate that I need to use one more inverter. Because otherwise one inverter I introduce, that I cannot do. If I am introducing one inverter from my side, so to compensate that I need to use another inverter, so that this logic function remains the same. Here A plus B was there, output will also be A plus B. So to compensate that I am using another inverter. So this is an AND gate. So one gate you will require here. To make this inverter, how many gates you will use? To make this inverter, another one gate you will use. And to make this inverter, how many gates you will use? Another one gate you will use. So how many gates are required? 1 plus 1 plus 1. 3 gates are required. So that is your answer. That is 3 gates. And how did we implement that? If you remember it clearly. So first A will be going through an inverter. This is an inverter. So this will be your A bar. Then B will be going through an inverter. That will be your B bar. And then there will be another NAND gate. This is a NAND gate only. So this is how you will implement A plus B. So to implement OR gate you required 3 NAND gate, and to implement AND gate you required 2 AND gate. To implement AND gate using NAND gate you required 2 NAND gate. Okay, let's go to the next one, that is AB plus C. So how will you implement AB plus C? Using basic gates. Using basic gates you need to implement. So how will I implement? This is my AB, A into B, then C will come. Sorry, plus C is there, no? AB plus C. AB plus C. Right? Now, what is the scene? You need NAND gate, right? You need NAND gate. So you need one inverter here. If I am introducing one inverter here, I have to introduce one more inverter here. Right? If I need to make this as NAND gate, then I have to introduce one inverter here. So if I am introducing one inverter, then another inverter I have to use here. Well and good. So what is this? This is one NAND gate. This is another NAND gate. And to make this one, you will need one AND gate. So one NAND gate, sorry. So how many total NAND gate you required? 3 NAND gate. Can you make this structure on your own? Yes. Look, again and again I will not be making, but you will be uncomfortable now, right? So C will come as C bar. This is A, this is B, this is C. So C bar is coming here and this is AB bar. So here what will come? Y is equals to AB plus C. So this is how you need to proceed in the problem. AB plus CD, which form is that? SOP. SOP form is that sum of product. So no need to worry. If sum of product form is there, no need to worry. Just implement that using basic gates. I I forgot to tell this thing, that sum of product, this is also sum of product. So if sum of product is there, then you don't need to worry. So AB plus CD. So again I will implement AB plus CD. So AB CD. So AB and CD multiplication I need to do, and then I will do the summation. Then I will do the summation. So what will be my answer? AB plus CD. But I need NAND gate. So if I need NAND gate, I have to introduce one bubble here. If I am introducing one bubble here, so another bubble will be introduced here. If I am introducing one bubble here, then another bubble will be introduced here. Say yes or no. Two bubbles I can introduce, right? Two bubbles if I introduce, it will be a simple wire only. It will be a buffer, and you can add a buffer anywhere. So this is one of the NAND gate. This is another NAND gate, and this is another NAND gate. So 3 NAND gates are there. So AB plus CD also I implemented using 3 gates. Try doing the next one on your own. AB plus BC. How many gates will be required? Pause the video and write down your answer. 3 gates, right? Which form is that? Sum of product. Do not change the form. Sum of product, don't change the form. This is also an AND gate, right? This is an AND gate only. Similar, ditto similar structure will be there. Ditto similar. AB, BC. A, B, and both will be same here. This will be your B, this is your C. So sorry. This bubble is not there. This bubble will not be there. What we are doing, we are just implementing AB plus BC. AB plus BC. Okay. So if I introduce a bubble here, another bubble I need to introduce, that will be introduced here. If I need to use bubble here, another bubble I will introduce, that will be introduced here. So AB plus BC. That will be our answer. So 1, 1 and 1. Answer will be 3. AB plus BC. Answer will be 3. Let's take more example. AB plus BC plus CD. Now my target will be to take something common. Here I can see something common will come. Here also I could have seen that something common can come. That if I take B as common, then A plus C would come. Can I do anything about it now? Can I change it? Anyhow, can I change it? Any changes can I do? No. No changes I can do. This will be again AB plus BC only. I will try to take common here. So B common I am taking. B into A plus C plus CD. Can I do anything about it? Nothing. Nothing I can do. Right? So again, the same way I need to proceed. AB, A into B, then B into C, and then C into D. Making sure that I have only 2 input gate, not 3 input. I have only 2 input gate. So I will use 2 input gates only. So this is A, this is B, this is B, this is C. So here I am getting AB plus BC. So AB plus BC. This is C and this is D. So this is CD. So here AB plus BC plus CD you are getting, right? So if you introduce a bubble here, then another bubble will come here. If you introduce a bubble here, another bubble will come here. If you introduce a bubble here, then another bubble will come here. Then to make it an AND gate, you need to introduce one more bubble. So if you are introducing one more bubble, then one more bubble will come. So 1, 2, 3, 4, 5 and 6. So answer is 6. Are you getting this point? Bubble I introduce, then another 2 more bubble I need to introduce. One bubble I introduce here, then another bubble I need to introduce here, right? To make it NAND gate, I need to introduce one bubble here. To make it NAND gate, I need to introduce one bubble here. So to compensate this bubble, I need to use one more bubble. So to make this one, this is a NAND gate. NAND gate, NAND gate, NAND gate, NAND gate. This is an inverter. To make an inverter, how many NAND gates I require? 1. So 1, 2, 3, 4, 5, 6. Answer is 6. Or how you could have done it? That to implement this AB plus BC, how many you require? 3. So let's just say I have implemented this function AB plus BC and I am denoting it as X. So X plus CD I need to implement. So to implement X plus CD, how much you require? Another 3. So for this you required 3 and for this another you required 3. So answer would be 3 plus 3 is equals to 6. In the examination, this is how also I can answer. Let's try doing this problem. Can you take anything common here? Yes, I can take anything common. So B will come common, A plus C. Plus, can you take anything common from here? Yes, I can take D as common. So A plus C. So what will be happening? B plus D into A plus C. Now very interesting thing I will observe here. What is that? If I assume this as X, B plus D as X. So X into A plus C. So what I need to implement? AX plus CX, where X is B plus D. I need to implement AX plus CX. How much this will require? 3. And how much this will require? This is what? This is an OR gate only. This will also require 3. So 3 plus 3, total answer will be 6. Are you getting this point or not? First I will implement B plus D. First I will implement B plus D. How will I implement B plus D? This is how I will implement B plus D. First I will implement B plus D. This is B and this is D. So B plus D will be implemented. And then B plus D, AX plus CX. So this is the X which I was talking about. So this X I will take and my target is to implement AX and CX. So X will go here and A will come. And this X only will come and C will come. This is x, this is a, this is c. So ax plus cx you are having. Then you can simply use a OR gate, or if I use OR gate, then simply inverters I will have to add. So this will be my final answer. This answer would be AB plus BC plus CD plus TA. So that will be the design. Okay. So as a designer, you need to think in this manner that B plus D, I can replace this with the X. So to implement that particular X, look, if I had been doing in this manner, that AB plus BC, this will require me 3. CD plus DA, this will require me 3. So this can be replaced with X and this can be replaced with Y. So X plus will require me another 3. So my answer would be 9. Right? 3, 3 plus 3, 9. But you need to use minimum gates. So for there, I first thought that if there is something common coming, yes, something common is coming. Then I got to know that if I replace this with X, then AX plus CX, this will require me 3. And X will another require me 3. So 3 plus 3, 6 will be my answer. That's it. Okay. So in this manner, I will be proceeding. More examples will come. Now examples will be tougher only. Okay. It will not go easy. ABCD. Very easy. What is the form? This is product term only. This is a simple product term. There is no plus. It could be product of sum, but there is no plus. So it is a simple product term. This is AB. अरे यार ABCD. A, B, C, D. Then multiplication of this A, B, C, D. So if I use inverter here, then another inverter I will have to use. If I use inverter here, then another inverter I will have to use. So this will require 1. This will require another 1, 2. This will require another 1. This will require 1 more. And how much this will require? 2. Right? This will require 2. So this will be, are you getting this point? This is AND gate. This is AND gate. How much AND gate requires? 2. AND gate requires 2 NAND gate. AND gate will require 2 NAND gates. So for this there will be 2. 2, 3, 4, 5, 6. Answer is 6. So in this manner we will be getting answer as 6. Okay, well and good. Let's try implementing this function. So first question, is this the form you want? You want sum of product, right? Is this sum of product or product of sum? This is product of sum. So this is not the form I want. So first thing is this. Second question, can you do anything about it? Can you change it anyhow? Then yes, I can change it. How will you change it? This is x bar plus y bar. Can I write it as xy bar? Xy bar into w plus z. Can I write in this manner? And I am assuming A as xy bar. My A is xy bar. So if I assume this A into w plus z, so that can be replaced with WA plus ZA. To implement this A, how much will be required? 1. And to implement this, how much will be required? 3. So what will be the answer? 1 plus 3 is equals to 4. So in 4 NAND gate only you will be able to implement it. How? Let's check that out. What I need to implement? What was my first question? I saw that this is not the form I require. Then I thought, can I do something about it? Yes, I can do. What I can do? X bar plus y bar, I can replace this as xy bar. So xy bar, I am assuming it to be A. So WA plus ZA. WA plus ZA I can implement in 3. That I know. AB plus CD I can implement in 3. AB plus BC also I can implement in 3. These will be in your brain, right? AB plus C, AB plus CD. That I can implement in 3 only. AB plus C, AB plus CD. These things. AB plus BC. I can implement all these in 3. So that will be in your mind. So here this is also is in my mind that I can implement this in 3, and this I can implement in 1 only. That's it. Now how I will do it? xy bar. So first I needed to implement xy bar, then xy bar into w, xy bar into w, and xy bar into w, xy bar into z. That's it. This is the answer. Xy bar came here, xy bar into w, xy bar into z, and then addition of this. So this will be my function. That would be x bar y bar into w plus z. So this question came in GATE examination, and you need to think in this manner. More examples we will see. What can come in future? Okay, this has already come. What can come in future? Let's see this example. Can you do anything about it? Yes, I can do. What you can do? You can take a bar common, b bar plus c bar. First question would be, this is the form you want. Yes, this is the form I want. This is the form that I want. Why you want this form? Because this is in the SOP form only. But something is coming common, so we will try something can we do, right? Something different can we do, because something is coming in common. Now what I can do? A bar, b bar plus c bar, b bar plus c bar. Can I replace this as bc bar? Right? So it feels like that I have reduced something. So I can easily make bc bar. I can easily make bc bar. Then I need a bar. Then I need a bar. And both combined can go into a simple AND gate. This can happen, right? This is my A, this is my B, this is my C. So here BC bar is coming into A bar, that would be A bar into BC. But you require NAND gate, so here you need to introduce a bubble. So if you are introducing a bubble from your side, then you need to introduce another bubble. So 1, 2, 3 and 4. That's the answer. If I had directly implemented, then what would be the issue? A bar B bar plus A bar C bar. So what I would have done? First I would have implemented A bar differently, B bar differently and C bar differently. It would have taken me 3. And then to make this function another 3. So answer would be 6. That would be wrong. So here intelligently I got to know that something is coming in common and I can reduce my number of gates. So that can happen. Okay. So in bar, if there is bar, then you need to think. You need to ponder there. You need to think something that something different can happen. Now this one is very interesting. What you can do? What you can do about this one? Very interesting. This is, let's just say this is x bar plus y bar. Can I write it as xy bar? Xy bar. So what I can do? AB into BC bar. What is AB into BC? That is ABC bar. So I just need to implement this ABC bar. That's it. AB bar plus BC bar is ABC bar. So when bar is coming, I will think about it. Okay. I will think something that what different can I do? Or this could have come in this manner as well. AB bar can be replaced as A bar plus B bar plus B bar plus C bar. Now you would be thinking, sir, there is no certain formula how you are doing it. There is nothing certain. Like study it from anywhere. No one will tell you that these many things as well, which I have taught, that see the SOP form, see if this is the form you require. If you don't require this form, take common. So there is no certain way. You have to think only here. Okay. You have to think. But I am from my side, I am dealing every possible example which can come in your examination. So this is the way you will be thinking. It could have come in this manner as well. AB, A bar plus B bar plus B bar plus C bar. So it can be replaced as A bar plus B bar plus C bar, and A bar plus B bar plus C bar can be replaced as ABC bar. So in NAND gate there is multiplication, so I would want multiplication, I would not want plus. My target is to get multiplication, and in one term only I am getting multiplication. Then what's better than that? So AB into C, AB into C, and then bar I need to take. So this is what I want, AB into C. So this is already an AND gate. To make this as an AND gate, I need to use one inverter. So another inverter I will introduce. So 1, 2, and 3. Answer is 1 plus 1 plus 1. That is 3. So in this way you can proceed. More interesting example will come. This one. What you can do about it? You can write it as AB CD bar, AB into CD bar, right? X bar plus Y bar is equals to X into Y bar. So AB CD bar. So AB CD, and then multiplication, and then bar. What you need? You need this to be an AB, A, B, C, D. If I am introducing one inverter here, so another inverter I will introduce. If I am introducing one inverter here, another inverter I will introduce. This is already an AND gate. 1, 2, 3, 4, and 5. So answer is 5. What about this one? A bar BC. Can you do anything about it? No, I cannot do anything about it. So I have to implement it. A bar BC, nothing more I can do about it. This A bar BC will be A bar BC only. So A bar and BC. This is my A, this is BC. So A bar BC. Answer will be A bar BC. But I need to use NAND gate. So this inverter will come here, another inverter will come here, this inverter will come here, and then another inverter will come here. 1, 2, 3, 4, and 5. So answer is 5. A bar BC, answer is 5. You cannot do anything about it. 1, 2, and this is the form you want. You want multiplication, right? You want multiplication. You don't want addition. You want multiplication. So if you want multiplication only, this is what you are getting. Can we do anything else? No, I don't think. So 5 you will be requiring minimum. Okay. So this is the answer, that you will be requiring 5. Let's see more interesting example. This is the interesting example, very interesting, and this can come in future. This hasn't come yet, but this can come in future. What you will be doing here? This is the form you want. First question, this is the form you want? No, I want sum of product, not product of sum. This is product of sum. I want sum of product. So what will I do? Let's do multiplication. If I do multiplication, what I will be getting? X bar Y bar, X bar Z, Y W bar plus Z Y. It is becoming more complex, right? It is becoming more complex. And if I say, like, if I assume this as A, and then I will do W bar plus Z. So this will take me 3. And how much A will take you? A is OR gate plus 1 inverter. So this will take you 4. So here your answer is coming 7. Are you getting this point? How did I write 4? X bar plus Y. So X bar will take you 1, and X plus Y will take you 3. And then if I assume this as A, so A into this will take you 3 plus 4, so 7 is the answer. That is also coming as pretty large. But this is not you want, this is also becoming very complex. So if nothing clicks, then take the double bar. What did I say? If nothing clicks, take double bar. That you need to take. Look, this is not the form I want. If I do this thing, this is becoming more complex. and then the another way I thought it is taking me 7 possible cases. So if nothing is clicking, I will take double bar. If we take double bar, let's see what happens. Double bar means like if I take a double bar, then it will be a only. So that's why I am taking double bar. So this will not change this Boolean expression. If this Boolean expression is a only, then if I am taking double bar, then it is not changing. It is becoming a only. So I will take double bar now. So x bar plus y into w bar plus z, double bar of that. So what this will become? X y bar into, okay, you are not habitual of it. So let's just say if this is A and this is B. So this is AB bar, right? So AB bar can be replaced as A bar plus B bar. So this is what I am going to do now. So x bar plus y whole bar plus w bar plus z whole bar, right? This is how it can be replaced. Now what is this? This is also x bar plus y bar. Then how it will be replaced? X into y bar. This we have already seen, right? And another whole bar is also there. So that whole bar we cannot forget. Another whole bar is also there. First we solved this bar. Then another whole bar is also there. So that whole bar also I implemented. Okay. So now this is a plus b whole bar. So that would be a into b bar plus w into z bar. And then another whole bar is there. अरे यार भाई, another whole bar is there. Now if I solve this bar, what I will get? X bar plus y, then w bar plus z. I will get the same expression. So why would I solve this bar? So this is the expression I am getting, right? X into y bar plus w into z bar to the bar. And this is what I want. What did I want? AB plus CD. Just bar is there. This is my A, this is my B, plus this is my C, and this is my D. This is what I wanted. And on the upper side there is a bar. So tell me how much this will take. Forget about the bar, how much this will take. AB plus CD, that will take 3. How much Y bar will take? 1. How much Z bar will take? 1. How much the whole bar will take? Another 1. Answer will be 6, not 7. The previous one were taking you 7, but here intelligently I thought that this is not the form I want. If nothing is clicking, I will take double bar. If I am taking double bar, then this is the form I am getting, and this is the form I am getting. So here I got to know AB plus CD is taking me 3, Y bar is taking me another 1, Z bar is taking me another 1, and then whole bar is taking me another 1. Let's make this structure. Very easy it will be. Y bar into X. Y bar into X, W into Z bar, then addition, and then whole bar. If you need to make this as AND gate, then another bubble will you will introduce here, and this as an AND gate, then another bubble you will introduce here. 1, 2, 3, 4, 5, and 6. Answer is 6. Okay, so that is the answer. So very important thing it was. This was a very good example as well. So this example I am expecting, if they are going to ask any question from this particular topic, then they will give this scenario this time, because they have already given this one. Why did they give this one? Because this is equivalent to XOR gate. This is equivalent to XOR gate. Okay, we will see it in the next lecture or in this lecture only, because time is passing. So this is equivalent to XOR gate, and this is equivalent to XNOR gate. This is equivalent to XNOR gate. So XNOR gate can be implemented using 5 NAND gate only, but this is being implemented using 6 NAND gate. So this is equivalent to XNOR gate. That's why I'm expecting this example can come. Okay. So let's solve the same kind of problems using NOR gate now. So in NOR gate, what is my target? If NOR gate is coming, I will be going towards POS form. So tell me one thing. POS form, then I will implement it using basic gates, and then I will convert basic gates into not NAND gate. I will convert basic gate into NOR gates. So to implement NOT gate, how many NOR gates are required? I just copied the page. That's why these are there. How many number of NOR gates are required? 1. For a OR gate, 2 are required. For AND gate, 3 are required. You can check it out. Here also I will write it down. Okay, I have already written it down. So 2, 3, we will check it out now. So how will I make A bar? How will I make A bar? Only 1 is required. This is how I will make A bar. This is A plus A, Y will be equals to A bar. How will I make A plus B? A plus B. A plus B I need to make. So simple to make A plus B. Wait a minute. To make A plus B, this is my A plus B. So this is my A plus B, but another inverter I have to use to make it a NOR gate. Then another inverter I will have to use, because if I am introducing an inverter, I will have to use another inverter to compensate it. So 1 plus 1, answer is 2. 2 is required. You can make it on your own, right? How will you make it? You can skip this part if you have already made it. This is how you can make it on your own. Y is equals to A plus B. Now Y is equals to AB. Y is equals to A into B. So what I will do? This is A, this is B. Y is equals to AB. But what you need? You need NOR gate. So for NOR gate, here you need to introduce a bubble and another bubble you need to introduce, because NOR gate is equals to, what is your NOR gate? This bubble will come upward, this bubble will come in front, and this gate will become NOR gate. Okay, so this is a NOR gate. So if I am introducing 2 bubble from my side, I need to introduce 2 more bubble. So 1, 2 and 3. So answer will be 1 plus 1 plus 1. Answer will be 3. And you can make it on your own as well. How will you make it? This is how you are going to make it. This is A, this is B. This is A bar, this is B bar. A bar plus B bar ka bar, that would be AB. Okay, so this is how you will be making it. Let's check out other. AB plus C, is this the form you want? Yes, this is sum. This is product of sum. This is sum only, no? A plus B into C plus 0. This is product of sum only. So this is the form I want. Yes, this is the form I want. So A plus B I can make like this, and then into C. So how will I make it? This bubble is there. Sorry, I need to introduce one bubble. Why do I need to introduce one bubble? To make it NOR gate. Then another bubble I need to introduce. Then this bubble also I need to introduce, so that it becomes a NOR gate. So another bubble I will have to introduce. One bubble I introduce to make it NOR gate, so another bubble I will have to introduce. then another bubble I will have to introduce to make it NOR gate, and then another bubble I will have to introduce because in the compensation of this NOT gate, right? So one NOR gate, another NOR gate, and another NOR gate. So 3 NOR gates are required. Do the same for AB plus B, A plus B into C plus D. So A plus B into C plus D. Right? This would be A plus B into into C plus D. So this will be like that. So 1, if I am introducing 1 here, so I will have to introduce one another here. So if I am introducing 1 here, another one I have to introduce here. This is A, B, C, D. 1, 2 and 3. So again answer will be 3. So this format we have seen. AB will take me 1, AB will take me 3. A plus B into C will take me 3. A plus B into C plus D will take me 3. So this is the form that we have already seen now. Okay. Now let's move to the next one. A plus B into B plus C. It will also take me 3 only. You can implement it on your own. A plus B into B plus C. A plus B into B plus C. So I will introduce, here also introduced, here also introduced, here also introduced. Okay. So what is the answer? 3. What about this one? Let's check. This one will take 6 as far as I think. This will take 6. A plus B, because this is the form I want. This is the form I want, so I will not change it. And nothing common and nothing like that, something is coming. So this is the form I want, so directly I will keep this form only. A plus B into B plus C. And then C plus D there you go. A, B, B, C and C, D. Bubble here, then another bubble here, bubble here, then another bubble here, bubble here, then another bubble here. If you are introducing a bubble here, then you need to introduce bubble here as well, right? So this is 1 gate, 2 gate, 3 gate, 4 gate, 5 gate and 6 gate. So answer is 6 gate. Okay, 6 is required. How you will do it? AB plus BC will take you 3. So I can assume this as X. So X into C plus D. A plus B into C. Then another 3 will take. So this will take 3 and this will also take 3. So answer is 3 plus 3, 6. So this is how also you could have solved it. Right? So this will take me 6. A plus B plus C into D plus C. This is the form you want? Yes, this is the form I want. So I have to solve it. A plus B and then plus C. This will come and then from here D plus E will come. D plus E will come and then both will be multiplied. So A, B, C, D, E. Okay. So one bubble I have to introduce here. So another bubble I have to introduce. One bubble I have to introduce here, and another bubble I will have to introduce here. This is an AND gate. This is an AND gate, sorry. So one bubble I have to introduce here, and another bubble I will have to introduce here. 1, 2, 3, 4 and 5. So answer is 5. Okay, 1, 2, 3, 4, 5. So that is the answer. So 5 is the correct answer. Now let's take this example, a plus b plus c plus d, a plus b plus c plus d. Can you do anything about it? Because this is the form I want. Sum I want. What I want? Product of sum. So in the product there is nothing else. This is the sum product. This is the sum term only. Only the sum. Sum is there. Are you getting this point? If I was implementing using NAND gate, then ABCD. This is the form I wanted. I did not do anything with that because this is the product term. So I want product term there. Here I want sum term. So I want sum term that I am having. So again, a plus b b plus c, and then both will be added. Right? So this will require 2. This will require 2 because this is a NOR gate. So to implement NOR gate, how much you required? 2, right? Here you say so. To implement NOR gate, to implement OR gate you required 2. To implement OR gate you required 2. So here also you will require 2. 2 and 2. Answer will be 6. Or you could have gone with the concept of inverter as well. If I use inverter here, then another inverter will come. So 1 plus 1, 2. Inverter here, another inverter. Again 2. Then inverter here, another inverter here. So 3. Right? So 1 plus 1 plus 1 plus 1 plus 1 plus 1. So answer would have been 6 only. Are you getting my point? How I am doing it? Look. This inverter I would have introduced, so another inverter I will have to introduce. This inverter I would have introduced, another inverter I would have to introduce. This inverter I would have introduced, so another inverter I will have to introduce. So 6 would be my correct answer. Now see this one. This is also very, very interesting. First question, this is the form I want? No. Can you do anything about it? Yes. X bar, Y bar plus WZ. This question can also come in the examination. That's why I have put a star mark there. This kind of question can also come. So this is not the form I want. So X plus Y bar plus WZ. Is this the way I can write it? Say yes or no. If I assume X plus Y bar as A, so A plus WZ. Now in the Boolean algebra, I will teach you one thing. What is that? Let's see it here. A plus B into A plus C. If you solve it, what you will get? A into A is A only. A into C is AC. B into A is AB. B into C is BC. From here I can take A as common. So 1 plus C plus B. I need to put the charge on. Wait a second. So A into 1 plus C plus B plus BC. So what you are getting? A plus BC. Right? What you are getting? A plus BC. So A plus BC can be replaced with A plus B into A plus C. This theorem is known as consensus theorem. What is the name? I don't know. Consensus theorem. I guess this is the name only. Because the name is not important. Consensus theorem, this theorem is known as. So A plus BC can be replaced with A plus B into A plus C. Because you solved it, you got A plus BC. Anything in addition to 1 is 1 only. So A plus BC I am getting. So A plus WZ can be replaced with A plus W into A plus Z. Say yes or no. How much you will require, and what is our A? This is the different thing. This is a complete different thing. Complete different thing. So better I should keep in a box. So this is a complete different thing which we will be learning in Boolean algebra. But here only I told you A plus B into A plus C. So A plus AC plus AB plus BC. So A if I take common, so I am getting A plus BC. So reverse way if I am writing A plus BC is equals to A plus B into A plus C. This multiplied with this into this this in addition to this A plus B into A plus C. So A plus W into A plus Z. What is my A here? Where my A is X plus Y bar. Where my A is X plus Y bar. A is x plus y bar. So A plus W into A plus Z. So A plus W into A plus Z, how much it will require? 3. And x plus y bar, how much it will require? 1. What would be your answer? 4. That's it. What is this? This is looking like a XNOR gate, right? This is looking like a XNOR gate. So to implement XNOR gate using NOR gate, you will require 4 only. So let's do it. How we will do it? X plus y bar. What we need to implement? First x plus y bar will come. Now from x plus y bar, I have assumed it to be A. So A plus W into A plus Z. How I can implement? Very easily I can implement A plus W. So one NOR gate, A plus W, and then another NOR gate, A plus Z, and then end of these two, right? So if I make bubble here, another bubble I will make here, another bubble I will make here, another bubble I will make here, and this bubble can be replaced with simple XOR gate only. XNOR gate. Sorry. Not sorry, XNOR, no. Sorry, NOR gate only. So 1, 2, 3 and 4. Answer is 4. Answer is 4. Okay. So this is the way we can go. So this was a very good example. Now another good example we will see. This example. First question, can you do anything about it? Sorry. Is this the form you want? No. Can you do anything about it? No. If nothing clicks, then take that double bar. And how this is looking? This is looking like a XOR gate. A bar B plus A B bar. So this is looking like a XOR gate. So take double bar. Take double bar. If nothing clicks, I will take double bar. Okay. What I could have thought? I could have thought that if I assume this as A, then what I can do? A plus W bar Z. So A plus W bar into A plus Z. So this will require me 3. This will require me 3. This will require me 1. This will require me 1. And X bar Y, this will require me 4. So my answer would have been 8. W bar will require me 1. This complete will require me 3. And X bar into Y, because XY will require me 3. XY will require me 3. And X bar will require me 1. So 4 plus 4, answer would have been 8. But in the lesser one, I can make it. In less, I can make it. And how I will make it? Let's check that out. Nothing is clicking. I took the double bar. So can you solve this bar? A plus B whole bar it is. So I can write A bar dot B bar and then whole bar. So X plus Y bar into W plus Z bar and then whole bar, right? So this is the form I want. POS form and then there is a bar. So X plus Y bar. X plus Y bar. W plus Z bar. And then there is a AND gate. And then there is a bubble. Okay. So how I can replace this? This bubble if I am making, another bubble I will have to make. This bubble I am making, another bubble I will have to make. This I implemented using standard gates. X, Y bar, X, Y, then Y bar will come. W here, then Z bar will come. And then addition of all these, let's forget these bubbles. Let's forget these bubbles. So X plus Y bar into W plus Z bar. And then whole bubble is also there. So this I made. Now, if I need to make it NOR, then I will use a bar. I will use a bar here. So if I use a bubble here, I will have to introduce another bubble here. I will have to introduce another bubble here. So now what is this? This is an XOR gate. Sorry, not XOR gate. This is a NOR gate. That itself is a NOR gate. So one, then another one here, then one here, then another one here, then one here, and then another one here. So answer is 6. Are you getting this point? This much of structure, only this much of structure. Forget about the bubble. Only this much of structure is one NOR. And to make this bubble, you will need another NOR. Right? You will need another NOR. Better I should have made this bubble somewhere here. Somewhere like this. To make this structure, I will need another one. 1, 2, 3, 4, 5, 6. So answer is 6. So this way we will be proceeding in these kind of problems. When we study K-maps, we will come back to these kind of problems. Look, these many examples, 15 plus 11, 26 examples, no one will teach you. Okay, I'm not saying that I am the best, nothing like that, but so many examples I have taught here. And if you are comfortable with these many examples, if you have built a good intuition, then if the question is coming, you will be able to solve it. And when we study K-maps, I will tell you another method to solve these kind of problems. Okay, there will be another method when we study K-maps. So two or three examples I will take there as well to implement any Boolean function using minimum number of gates. So that's it. This is the complete concept. Now we will implement XNOR gate and XOR gate using, now we will implement XNOR and XOR gate using NAND gate and NOR gate. But before that, one important thing is there. So you know this thing, right? A XOR B is A bar B plus AB bar. This can be replaced in another way. How it can be replaced? A bar plus B bar into A plus B. If you solve it, what you will get? A bar into A into A, plus A bar into B, plus A bar into B, plus B bar into A, plus B bar into A, plus B bar into B, B bar into B. A bar into A is 0, plus A bar B, plus B bar A, and B bar into B bar is 0. So A bar B plus A B bar. This is the answer. So these two are same only. How will you remember it? So you will remember it that this is SOP form, sum of product form. If I need to write in product of sum form, then I will remember XNOR. So what is the answer of XNOR? This is the answer of XNOR. A bar B bar plus AB. So A bar plus B dot A plus B. This is how I will remember it. Say yes or no. And this is also which form? Sum of product form only. If I need to write in product of sum form, then how will I write? I will remember XOR. So A bar plus B into A plus B bar. That's it. Okay. So is this the way can I remember these two formulas? Say yes or no, right? So let's solve this problem. You need to implement XOR gate using NAND gate. I am implementing XOR gate using NAND gate. So A XOR B is there. A bar B plus A B bar. First question, is this the form you want? Yes, I want this form. This is sum of product form. But bar is there. Can you do anything? Yes, I can do anything. What I can do? I remember another form of it. What is that? That form is A bar plus B bar into A plus B. So I will think about this form as well. If I think about only this form, then what will be my answer? A bar B plus A B bar. How much this will require? 3. How much A bar will require? 1. How much B bar will require? 1. My answer would be 5. Okay, let's hold on to this. My answer here, if I directly go by this method, my answer will be 5. That I need 5 NAND gate to implement XOR gate. But if I go by this method, A bar plus B bar into A plus B. Can I write A bar B bar as A bar plus B bar as A B bar into A plus B? Can I write in this manner? Say yes or no. And if my A B bar is X, if I am taking A B bar as X, then can I write it in this manner? That my X is equals to A B bar. So what it would be? AX plus BX. So this will require me 3 and this will require me 1. So what would be my answer? 3 plus 1 is equals to 4. So in 4 only I am able to implement. Did we see the same kind of example here? Say yes or no. The same kind of example here. XY whole bar into W plus Z. So with respect to that example, Gate framed this question. So that's why I am thinking with respect to some another example, they will frame this problem. What is this example? This example is based on XNOR gate. Or they can frame these problems. Problem 10, problem 9. So these problems may come up any day in your examination. This is what I am thinking. Okay, if some question is coming, then these two problems will come. And nowhere in the gate industry you will find these two problems. Okay, this I framed myself only. One problem you will find that is coming from the gate examination only, but those three problems that you will not find, because that I framed here only and then I solved that. Okay, and I'm pretty sure my answer is correct there. So this is the way we can implement, right? Okay, so answer is 4. So how we will implement? First we will implement AB bar and then this we will implement. So this we have already seen. So this is A, this is B. AB bar will come here and A will come here and AB bar will go there and B will come here. So this is our XA plus BX. This is our XA plus BX. This is AX plus BX. And this is X. Now tell me one thing. If this gate has delay TD and this gate has delay TD and this also has delay TD. So if I apply A and B here, let's just say I apply A and B at t equals to 0. So after how much time I will get my output? TD plus TD plus TD, because TD and after TD time here there will be some input and at t equals to 0 only here there will be some input. So this will wait. This input will wait for this because this input will come after TD time. So after TD time this input will come. So after TD plus TD, after 2 TD you will have something here. And after TD plus TD, after 2 TD you will have something here. And 2 TD plus TD, that will be 3 TD. So after 3 TD time you will get your output. So there are 3 levels, right? Level 1, level 2, level 3. There are total 3 levels. This also I can remove. Level 1, level 2, level 3. So this is known as 3-level assembly. Okay, 3-level assembly. So if I introduce something at t equals to 0, then I am getting that output after 3 TD delay. So my output will be I am getting after 3 TD delay. Okay, so propagation delay of one NAND gate is TD, then total propagation delay would be 3 TPD. Well and good. Now we will make XNOR gate. So there could be 2 ways of making XNOR gate. This is the first one. In first one, what we are doing? We are taking A XOR B, and then simply we are taking the bar. So here we are getting A XOR B, right? This is our A XOR B. This much structure. The same structure I have copied here. A XOR B. And then A XOR B, and then another. What is this? This is an inverter only, right? This is an inverter. This thing is an inverter only. So here what you will get? A XOR B bar. Or you can say A dot B. How many levels are there? Level 1, level 2, level 3 and level 4. So this is what? This is 4-level assembly. This inverter I will remove. This is 4-level assembly. So if propagation delay of each NAND gate is TPD, then what will be the total propagation delay? That would be 4 TPD. Okay. If propagation delay of each NAND gate is TPD, then what will be the total propagation delay? That will be 4 TPD. So now my question is this the best way of implementing this function? So your answer is no. This is not the best way. There could be another way as well. Look, how many NOR gates you required? Sorry, how many NAND gates you required? How many NAND gates you required? 5 NAND gates. 5 NAND gates. Here, how many NAND gates you required? 4 NAND gates. 4 NAND gate. 4 NAND gates. Right? And here you required 5 NAND gates. So the number of gates are 5, that is good, but the propagation delay is 4 TPD. Can I implement it in another way? What that way could be? What is your y? Y is A XOR B, and that can be written as A bar B bar plus AB. So A bar B bar plus AB. So A bar B bar plus AB, let's just say it is XY plus YZ, XY plus WZ, XY plus WZ. How much this will take? 3. And A bar will take 1, and this will also take 1. B bar will also take 1. Basically, this will take 1, this will take 1, and this combined will take 3. So 3 plus 1 plus 1. So answer is 5. So in 5, using 5 gates only, I can implement XNOR gate, but in a different manner. So I will check there how much delay I am getting. Using 5 gates only, I can implement my XNOR gate using 5 NAND gates only. But that would be a different structure. This is a different structure. How did we get this structure? First we implemented XOR gate, then we just simply inverted it. That's it. But there could be another way. A bar B bar plus AB. Right? There could be another way. So what that way would be? First we will take A bar, then we will take B bar. So A bar B bar, and then we will do this structure. We will do this structure. Basically, let's make it here. A bar, B bar, and then multiplication, and then AB, A into B, and then what is there? Then there is addition. Right? So here if I implement one bubble, another bubble I have to implement. One bubble here, another bubble here. 1, 2, 3, 4, and 5. This is A, B, C, D. So answer is 5. So this is the answer. So in the same way I have implemented this. Right? Now tell me, if this has TPD delay and this has TPD delay, all are having TPD delay, then how much will be total delay? 3 TPD, right? Because this is level 3 assembly. If I apply at t equals to 0, if I apply input here, then after TPD time you will get here, after TPD time you will get here. So TPD time after A bar and B bar will come. So after more TPD time, at 2 TPD time you will get something here, and this you will get after TPD time, but this has to wait for this one because this will come after 2 TPD. This is there after 2 TPD, this is there after TPD. So 2 TPD plus TPD will be 3 TPD. So this is level 3 assembly, level 1, level 2, level 3. So this is 3 level assembly. So you made your XNOR gate using NAND gate only, but here your delay was 3 TPD and here your delay was 4 TPD. So which is a better method? This is the better method, no? Here I am getting less delay. But in my design, let's just say I am designing something, and in my design, if I need both XNOR gate and XOR gate, if I need both gates, then I will use this structure. Because from here I can get the function of XNOR gate. Sorry, from here I can get the function of XOR gate, and from here I can get the function of XNOR gate. But if I am designing only XNOR gate, if I need only XNOR gate, then I will use this function. Because in between here you cannot get XNOR gate, right? In between here you cannot get XOR gate, sorry. In this structure, in between only you can get XOR gate. But here at this node, will you get XOR gate? No. You will separately have to make it. So in my design, if my requirement is I need XOR gate and XNOR gate both, then I will go with this structure. Otherwise, if I only need XNOR gate, then I will go with this structure because here there is minimum delay. And also cost is same only. Here also you are requiring 5 NAND gate. Here also you require 5 NAND gate. So cost is same. Here 5 NAND gate is there. This is also taking 5 NAND gate. So cost is same. So based on the requirement you need to see. If you only require NOR gate, then you will go with this particular structure. Okay. Not NOR, XNOR. Yeah. So that's it. Now we will make implementing XNOR gate and XOR gate using NOR gate. So first we will implement XNOR gate. First we are implementing XNOR gate using NOR gate. So A bar, B bar plus AB. Is this the form you want? My question is this the form you want? No, I don't want this form. Because I want sum of product, right? What I want? Sum of sorry, product of sum. I am implementing using NOR gate, so I want product of sum. So what I can do about it? A bar B bar plus AB. What I can do? I can replace this as AB bar plus AB, right? And if I assume AB bar as X, AB bar as X. Sorry, this is not AB bar, this is A plus B bar. So if I assume A plus B bar as X, so it would be X plus A into X plus B. How did I write X plus A into X plus B? By consensus theorem. Here I taught this theorem, no? Here only. X plus AB. So X plus A into X plus B. Right? Here I am writing X plus AB, or I can write P plus QR. P plus QR is equals to P plus Q into P plus R. So this is how I wrote it. Now X plus A into X plus B, that can be made in 3. And this can be made in 1. So what is the total answer? 3 plus 1. That would be 4. So first I will make A plus B bar and then I will make this structure. So A plus B bar, here this is my A, this is my B. If this is having TPD delay, so here I am getting A plus B bar, right? This is my A, this is my B. And then this is the structure which will eventually it will give me A XOR B. Okay, or you can say A XOR B bar. So all are having TPD delay, then my answer would be 3 TPD, right? So total delay will be 3 TPD. Now what I will make? Now I will make XOR gate. Sorry, XOR gate. XOR gate I can make. This is the way 1. What is the way? Simply XOR gate. So simply I can make XOR I have already made. So just take the bar. So this is XOR. A XOR B. So I will just take the bar here. So this I will get. So if this is having TPD delay, then total delay would be 4 TPD. Right? Total delay would be 4 TPD. Now the next one. Now I need to make this. Now there could be 2 ways. In the same manner, there could be 2 ways. Here, if each delay is TPD, then total delay will be 4 TPD. And what is this? This is level 4 assembly. Level 1, level 2, level 3, and level 4. So this will be level 4 assembly. Right? Now what could be the way to? First I will see this, and my question will be, is this the way you want? No, this is not the way I want. Right? Because I want product of sum form. Product of sum. So for product of sum, I am having this A bar plus B bar into A plus B. So combined this will take 3, right? Combined this will take 3. This will take 1 and this will take 1. So total it will take 3 plus 1 plus 1. So total 5 will be required. So A bar plus B bar into A plus B. So 5 will be required. So A bar, this is your A bar, B bar. So A bar plus B bar, A plus B, and then multiplication. So if you introduce one NOR gate here, sorry, one NOT gate here, then you have to introduce one NOT gate here as well and one NOT gate here as well. So this will take 1, 2, 3, 4 and 5. So answer is 5. So this will be the structure. A bar, B bar. So this is level 3 assembly. Level 3 assembly. Okay. So if this is taking TPD delay, then how much delay this will take? Because this is 1 level, 2 level, 3 level. So 3 TPD delay it will take. So based on the requirement, you will see what you need to implement. If you need both the functions, then you will take this this particular structure. But if you need only XOR function, then you will take this particular structure. So that would be your answer. Okay. So TD delay here, 3 TD delay. Sorry, 3 TD delay in this one and 4 TD delay in this one. So based on the requirement, you need to check. Okay. Now this is the question. 2 input XOR gate and XNOR gate are implemented using minimum number of 2 input NOR gate and NAND gate respectively. Find the minimum propagation delay. So 2 input XOR gate is implemented from 2 input NOR gate. 2 input XOR gate is implemented from 2 input NOR gate, and XNOR is implemented from NAND gate. So how many it will be required? How many will be required? 5 gates. Here also you will require 5 gates. What will be the minimum propagation delay? Minimum propagation delay, for that you need level 3 assembly. You need level 3 assembly. So answer will be 3 TPD, not 4 TPD, right? Answer will be 3 TPD. 4 TPD would be wrong. This answer would be wrong. Why this would be wrong? Because this is the minimum delay. If we need minimum delay, then I will go with this structure, not with this structure. When I will go with this structure, if I need both the operation, XNOR and XOR. But if I need only one operation, then I will go with this structure. Okay. Now let's implement NOR gate and NAND gate using like NOR gate using NAND gate and NAND gate using NOR gate. Very simple, right? What I need to implement? What I need to implement? A plus B bar. This I need to implement. A plus B bar. NOR gate using NAND gate. Using NAND gate, right? If I need to implement, let's do it again. First I will take A plus B and then I will take bar. So if I introduce a bubble here, then another bubble I will have to introduce here. If I introduce bubble here, then another bubble I will have to introduce here. So this is one of the NAND gate. 1, 2, 3 and 4. So what is your answer? Answer is 4. So you will require 4. How will you implement it? Very easily you can implement. This is your A bar. This is your B bar. And then it will go here. Sorry, this is not bar, this is A and B only. This will go here and then another bar will come. So that's it. This is the way you can implement. And what about this one? What do you need? A into B and then another bar. So you have to introduce a inverter here, you have to introduce an inverter here. So another inverter you have to introduce, another inverter you have to introduce here. So 1, 2, 3, 4. So answer will be 4. How will you introduce? How will you make it? These should be simple by now. Okay, you should be comfortable with these kind of problems at least. This is your A. This will be your P. I am simply making an inverter only. Then another NOT gate will come. That's it. Okay, so Y is equals to AB bar. Now let's make a table and let's write down the minimum number of gates required. And how will you remember it? That also I will tell. So to implement NOT gate, NAND and NOR both are required, only one only. Now NAND is near to AND, right? NAND AND. So it will require 2. And NOR is near to OR. So this will require 2. NAND is far to OR. This will require 3 and this will require 3. Can you remember it this way? NAND is near to AND. So it will require 2. NOR is near to OR. It will require 2. Rest of them will require 3. NAND, from NAND to NOR, very far away. NAND to OR is requiring 3. So this will require 1 more, 4. NOR to NOR. NOR to NOR, 1 only. NOR to NOR, 1 only, because NOR is itself NOR, right? NAND to NAND, 1 only. Now NOR to AND is 3. So this will require 4. Now, how you will remember this XOR and XNOR? So what you will remember? NOR to XNOR you will remember, because only you need to introduce one word, that is X. So NOR to XNOR will take 4. So from node to XOR will take 5, and here it will be opposite. This will take 4, this will take 5. Did you understand what did I tell you? You will remember only one thing, that if let's just say in the examination question is coming, how many NAND gates are required to implement XNOR gate? This question is coming. Now you are blank. So what you will do? Okay, I know from NOR to XNOR only one extra word is there. So from NOR to XNOR it requires 4. So from NAND to XNOR it would require 5. That's it. Opposite are there, no? Opposite are there. So from NOR to XNOR you will remember. This will require 4. So that will require 5. From NOR to XNOR it requires 4. So from NOR to XOR it will require 5. And from NAND to XOR it will require 4. Opposite are there. 4, 5 are opposite. So this is the table which you need to remember. Okay. These tables, this is the table which you need to remember. Well and good. So in that manner, this part is completed. Now next what we will see? We will see something. We will see about Boolean algebra. So next we will see Boolean algebra, or yeah, now we need to see concept of delay. That is very important. So next we will see concept of delay. So we will draw the timing diagram based on concept of delay. Also we will see Venn diagrams as well. So logic gates are not completed, but this was a very important lecture and I hope you must have understood a lot of new things here. So this lecture is completed. Next we will see concept of delay and logic gate and Venn diagrams. Okay, so let's meet you in the next lecture.